Alright, so this particular video is about normal distributions, and in particular we're going to talk about applying the 68, 95, 99.7 rule. So just I'm going to give you a little recap about what's going on inside of a normal curve, standard deviations and stuff like that, and then we'll explain what this rule means. So here we have a kind of graph of normal curve. I'm never an artist, so this stuff's always better in a book than in mine. Remember that X bar is the mean of my sample. Okay, mean of my sample. So first thing that you need to do before you start working with any of this stuff with a normal distribution is find your average, mean of the sample, and S is the standard deviation. Okay, and again, this is on the sample, not on the population. There are different variables for the population than there are for the sample. That's why I'm making a big deal, because in a little bit we'll get extra variables that we would use if we were working with the population instead. So remembering that there's a, let me give you a little definition for standard deviation. Standard deviation this is a number that represents what we would consider kind of a natural break in my data where we expect to find most of our data points. Okay, so what that means is inside of, in our case, it's going to be 2 standard deviations. We will say those are expected values. Okay, again, there's that word expect. Okay, so all data points within 2 standard deviations are expected. Okay, and again, I say 2 standard deviations. That's for our purposes. Some stats books look a little more carefully. Some use 3 standard deviations, some use 2. So for our purposes, we're going to do 2, but just realize that that might vary from book to book or from teacher to teacher. Okay, outside of 2 standard deviations is where our outliers will be. Outliers fall. Okay. Okay. So that's all kind of what we've already talked about. But here's that 68% rule. Within 1 standard deviation, we expect to see. There's that word expect again. Okay, it means if it's normal data, which we wouldn't be using the normal curve if it wasn't a normal data. If it's normal data, we would expect to see I'm sorry. Yes, we would expect to see 68% of all normal data points. Of all normal data points. Okay. And some books will talk about the median instead of the mean. Just remember, if we're talking about normal data, the median and the mean are going to be at the same spot, so it won't matter. So again, here's the idea. 1 standard deviation above it, however big that is, and 1 standard deviation below it. So they didn't say within 1 standard deviation above or whatever. They said within 1 standard deviation. So if this is my mean, then 1 standard deviation above it, 1 standard deviation below it. Within that space, that area of the curve, we expect to see 68% of our data. Now think about it, that's the tallest portion of the graph, right? So because we're looking at the tallest portion, we would expect a huge chunk of our data to be in there. So that should hopefully make sense. So that's 68%. Okay. All right, so 2 standard deviations. Also, 2 standard deviations hold 95% of the data. Of my data points. Okay, so again, here's my mean, 2 standard deviations above. Here's another standard deviation, and 2 standard deviations below. Okay, so within that crunch of stuff, let me do this. We expect to see 95% of our data. Okay, well that again should hopefully make sense because again we're looking at a huge chunk of the data right there in the center of my graph, and that's where the middle portion of my graph is looking at. So think about like if we were in a box and whiskers, we would expect 50% of our data inside that box, right? Well, here we're saying 68% within 1 standard deviation, 95% within 2 standard deviations. And remember, our rule that we learned when we were talking about standard deviation was if you're within 2 standard deviations above or 2 standard deviations below the mean, you're an expected value, right? So everything, what they're telling me, everything that is in the central 95% of my data, those guys are expected values. It's these that are way out here on the tails that might be trying to pull my data one direction or the other, right? That might be trying to skew my graph. Those are the ones we're not expecting, and maybe those are outliers, right? So, well, for our purposes, if they're above 2 standard deviations or below 2 standard deviations from the mean, we will call them outliers. They're going to be automatically dumped out of our data set. Okay, which, by the way, when I dump points out of my data set, I have to refine the average, and then I need to do it again, right? So this is kind of one of those things that you have to keep on balancing until you figure out exactly what your data set is without data points. Okay, so that's the 2 standard deviations. But wait, the rule was that I mentioned at the beginning, 68, 95, 99.7. So the 68% is within 1 standard deviation. The 95% is within 2 standard deviations. So of course what? The 99.7, that's within 3 standard deviations. So real quickly, that would look something like this. 1 standard deviation above, 1 standard deviation below. This gives me 3 standard deviations below, 3 standard deviations above, and we said that would be 99.7% of our data. So that's why I said some people use 3 standard deviations because that's 99.7% of our expected values for sure. If you're not in that 99.7%, you're way out there on the tails, and so they definitely consider those outliers. Real quickly, okay, so let me get this bit in, and then we'll talk a little bit. We'll do a little bit of math. I don't want to confuse anything, but I want to make sure everybody's really good with these numbers. So, data points within 3 standard deviations of the mean account for 99.7% of all data points in this set. Okay, so let's get that in there and make sure everybody knows. So within 3 data point set, or I'm sorry, within 3 standard deviations, we're talking about 99.7%. So let's think about that. If this is 99.7% of all my data, what percentage is left over? Well, if all of my data is 100%, minus 99.7%, right? Then that's going to be 0.3% of my data left over. And I'm going to say that's on the tails. Okay, so these are my outliers. And they're the very most extreme, highest and lowest values. And so they're the farthest away from the mean, and there's not much there. Okay, so these are on the tails. In this case, the graph that I've been showing you, the normal distribution, is a two-tailed graph here, right? I've got both tails going on. So if 0.3% is on the tails, okay, let's think about this for a second because I want us to do a tiny bit of math. 0.3%, that means they're over here and over here, but I've got two tails. So what does that mean for me as far as portions that are on each tail? It's 0.3 in the tails, but I need to know each tail, or I want to know each tail. So if you would divide that by 2, right? Okay, and then we know that what? 2 into 30 goes 15 times. Okay, 2 into 3 once, carry the 1, 10, 2 into 10, 5. Okay, so it's 0.15. So the percentage that's on the tail here is 0.15%. Okay, that's really tiny. Okay, it's not 15%, it's 0.15%. Okay, because we've got 99.7% in here. I've only got 0.3% left to deal with. So 0.15%. That's a really tiny percentage. And so we expect that only the farthest out of my outliers would be in those percentages. Okay, well, let's do something similar. Let's start in the center and look at this 68%. And see that I've got one standard deviation above the mean and one standard deviation below the mean. And let's talk about what that means percentage-wise for each of those bars, if you will. 68%, those are equal standard deviations, right? They're the same area. So 68%, how would I get for each of those bars? There's 2 bars. 68% divided by 2, right? Well, 68 divided by 2 is 34%. So I've got 34% of my data and 34% of my data. Okay. All right. So for instance, some of the problems that we're going to, so hopefully that makes sense, split it up in halves. Some of the problems we're going to be working on are going to say, what percentage of the data is below whatever this mark is here? Say it was just the 3 standard deviations above the mean. Well, we know it's 99.7% within the 3 standard deviations, right? That's the 99.7. But if I said below this point, I would have to do the 99.7 plus the 0.15%, right? So 99.7 plus 0.15, that's 99.85%. Okay, so we're going to have to do maybe a little bit of addition, maybe a little bit of arithmetic here. Okay, so let's keep going. In here, I've got 95% of my data, but I already accounted for 68% of it right here. So what does that leave me with? 95% minus the 68%. I don't want to do arithmetic in my head. It's never good. So what is that, 7? 27%. Please check my arithmetic. Let me do that real fast just to make sure. Since this is a recording, I don't want to mess it up. 95 minus 68. Yeah, 27. Okay, so I've got 27% inside of this 95% that wasn't accounted for in here. Okay, that means inside of here, right? Those 2 bars, so to speak, that's 27%. My 27% that's left over. So then what is in each of those bars? Well, again, it's 27%. I would divide by 2, right? It'd be 13.5%. Please do the arithmetic and double check me. Okay. So it looks like 13.5% over here and 13.5% over here. Now, I can always double check myself by adding things back up, right? 34 and 34 really is 68. 13.5 times 2 really is 27. Add that to 68. I hope I get 95. Okay, but by doing this, I can figure out what percentage is in each little piece. I've got 2 more to do, so let's do them real quickly. Think about it. 95% is taken up in these 2 standard deviations from the mean. I've got 99.7%, so what's the difference there? Okay, 0.7. 4.7%, it's not much, right? That's in these 2, okay. But again, it's in these 2, and I want to know how much is in each one, so we should divide by 2. 2.35%, again, check my arithmetic, always, but I think it's 2.35%, 2.35%. All right, let me do some math real fast on my calculator and double check myself just to make sure, just because this is indeed a video and I don't want to lie on YouTube, okay? So 2.35, 2.35, that's correct. So now if I have something that says how many data points or what percentage of my data points are below the 2 standard deviations above, well, above this mean, then I can say, well, it's this 95% for sure that's in these 2 standard deviations, plus the 2.35, plus the 0.15. All of that percentage is the percentage of the data that's accumulated to the left-hand side of whatever my point is. And of course, if I come here, it should be everything except for this 0.15. Sometimes people go, oh, I'll just subtract this from 100 and whatever's down there, that'll be there. And that's fine too. You can totally do that kind of arithmetic for sure. All right, so there's just little tricks that you can pick up here. Of course, below the maximum here, we should have 100% of our data points showing up. Okay, so it's called below a certain mark or to the left of a certain mark. You might hear it called the area underneath this curve, well, where the curve is the normal curve, right? So how much area is underneath the normal curve within 1 standard deviation of the mean? Well, that's 68% of my data point, okay? Or 68% of this curve. That's the way they think about it. All right, so yeah, that's just kind of the idea behind that. Let me see if I have an example. Nope. I don't have anything where they actually asked me a question about this. So, okay, this is going to lead to z-scores. All right, my questions are about z-scores, so we'll scoot forward just a tiny bit. What the heck is a z-score? Well, a z-score is our 3rd way of figuring out if we have an outlier. So how do we know if we have an outlier? In our data set, there's 3 ways. We now have 3 ways of finding out. Okay, number 1, do your box and whiskers. Okay, we did that maybe a week or 2 ago. Find your IQR. That's the high part of the box, or your Q3, minus the low portion of the box, which is your Q1. I'm out of space there. Let me put it here. Q3 minus Q1. Okay, multiply by 1.5. Go watch the video on box and whiskers if you're not sure. It's one of the more modern graphs that we had. Okay, Q3 plus 1.5 times the IQR. That gives me a fence number. Any data point above that fence number, and I have an outlier. Q1 minus 1.5 times the IQR. That gives me another fence number. Okay, And we know outside of our fence numbers are outliers. So any data point that's outside of our fence numbers, that's an outlier. Okay, that's our first way. Number two, we did this the other day, standard deviation. Standard deviation. Okay, so we got to find the standard deviation first of all, and we know this is a little bit of a process. Fortunately, for some of these z-score problems we're about to do, we need the standard deviation, but they often will give them to us, so we don't have to do this calculation because it just takes time, right? Okay. And what you'll find as you use some of the statistical software like StatCrunch or SPSS or R or something like that is if I have a lot of data points, it's so much faster to just stick them into the stat software and have that do it for me. So standard deviation is the square root of the sum of all my individual data points minus the mean, find that difference and square it, and then add all those differences squared up. Divide by n minus 1. Okay, that's that formula that we did. And so what we said was the mean plus 2 standard deviations. Inside of there, we're okay. And the mean minus 2 standard deviations. Inside of there, we're okay. These are indeed considered our normal data points or my expected values. Okay, outside of that is outliers. It's that outside thing that gets us the outliers. And now for our third technique, this is the one we're going to look at now, is z-scores. Okay. So first of all, we need a little formula. Z equals x sub I minus x bar. Divide by s. Okay, where we know what all these things are, right? X sub I is an individual data point. X bar is our mean, and s is our standard deviation. So this looks like z equals individual data point minus the mean, minus the mean, divide by the standard deviation. Okay, so that's what we got. All right, and what this will do is this gives me a number value, and we're going to look and see what we get, and basically it compares the difference between my data point and the mean to the standard deviation, and it will tell me how many standard deviations. Z tells me the number of standard deviations a data point is from the mean. Okay, that's what it tells me. All right, and why do we care? Because if we find out that it's 2.5 standard deviations away from the mean, then I can use this idea we had in number 2 and say, oh, look, it's bigger than 2 standard deviations away from the mean. It's an outlier, okay? But this will actually give me a number value that tells me how many standard deviations. And it's because I'm doing this ratio, this comparison to the standard deviation. So like I said, a lot of these problems, they'll go ahead and tell me the standard deviation, because the point of this problem is not to find the standard deviation, it's to use the standard deviation. So here's an example. Okay, and this one says, if you know that your mean is 178 and your standard deviation is 41, okay, then find your z-score. Okay, that's what it wants me to do. All right, this is not so terrible. Find your z-score if, oh, sorry, I'm not through. If a data point is given as 190. All right. Okay, so find that z-score. Well, we got to do the arithmetic here, right? So again, come up here, z equals my data point, individual data point, x sub I. Well, my data point is 190, right? Minus the x bar, well, that's minus my mean, which we know the mean is 178. And divide by my standard deviation, my s, which is 41. Okay? So I just need to do a little bit of arithmetic here. That's what, 22? Nope, that's not 22. That's 18. Nope, 12. Sorry. Plus 2 would give me 80, plus 10 would give me 90, 190. So it's 12 divided by 41. Okay? So the nice thing is that we know this isn't bigger than 2 because 12 is smaller and it's on the top. That gives me a z of 0.2926. Okay? So what does this tell me? It's definitely not bigger than 2, so it's definitely not an outlier, but think a little bit more. This is 0.2. That means it's within 1 standard deviation of the mean. Okay, which we should have known that because it's really close to 178, right? And with a big standard deviation like 41, for sure it's going to be inside of there, so that makes sense. All right, let's do another one. What if we had the same mean and the same standard deviation, but our data point is 100? Okay. Then I do the same calculation, right? It would be z equals, but instead of the 190, I've got a data point of 100 minus 178, because my mean's still the same, divide by 41. Okay. Well, look at this. Whenever I do it, 100 minus 178, that's going to give me a negative. Now, remember what we said last time. When you're negative, that doesn't mean something bad. All it means is that my data point is below the mean, which we know it is because it's smaller than 178. So that's okay. So that's what that negative does for me. But also look here, 78 divided by 41, right? So when I do that, I get a negative 1.9. Okay, so that was not an outlier up there. Okay. What about this one? Nope, still not an outlier, right? Because this is within 2 standard deviations below the mean. Okay, the other one was above the mean. This one's below the mean. 190 is bigger than the mean there. 100 is smaller than the mean here. So it's still within 2 standard deviations below the mean. And so we say, oh, nope, it's not an outlier because it's within 2. Now it's getting close, right? It's very close to 2, but it's still not an outlier. Okay, so nope, still not an outlier. We're still not going to do it. Have a problem here. All right, so let's keep going on. We're dealing with standard deviations here. Okay, what if I gave you the example? So I'm going to pull a new mean and a new standard deviation. And this one said that my mean was 65 inches of whatever it was, and that the standard deviation was 2.5 inches. Okay, now notice that this standard deviation is a lot smaller than the last one we had. The last one was 41. This one's 2.5. So what does that mean for us? That means that my data is more closely clumped together, right? It's more consistent because the width of one standard deviation here in that last problem, that one standard deviation was 41 units wide, but now it's only 2.5 inches wide, right, or 2.5 units wide. So it's a lot closer than when we had 41 for our standard deviation. All right, so what does that mean for us? That means that our data is more closely clumped together, which means if I have one that's very far out of line, it's actually probably going to be an outlier a lot easier, right? It's easier to get outside of that 2.5 units worth of standard deviation than it is to get outside of 41 units, which is basically what that means. Okay. All right, so here's the question. This is the average height of people in whatever class. So it says if Susie is 73 inches tall, find her z-score. Okay, and then we want to know, is she an outlier? Okay, and by the way, this was the average height of women. Not men, but women. Okay, that's what that data set was that I stole this from. Okay, so let's find our z-score. That's the first thing. Well, z equals the individual data point, which in this case is Susie's height, which is 73 inches, minus the mean or the average height, which is 65. Divide by the standard deviation, which is 2.5 inches. So what they're saying here is that women are normally pretty close to each other's height, and so we have a very small standard deviation for that. Okay, well, let's see. 73 minus 65, that's 8 over 2.5, and whenever I divide that out, I get a 3.2. Double check me, but that's 3.2. All right, so whenever I see that, I say, okay, is Susie an outlier? So this tells me that she's more than 3 standard deviations above the average, the mean. So what does that tell me about Susie? Susie is an outlier. Yes. She's bigger than 3 on the standard deviation. Bigger than 3 standard deviations on her z-score. So we know it's bigger than 2. Boom, outlier, done. I don't have to do much more with it. Okay. So here's a problem. This one is actually a problem that allows me to work with those percentages. So let's look at it. So we're talking about this same problem, average height of women, and I'm going to get us in here a normal curve. And I'd like to actually work with the numbers that they've given us, so let's do it. So here's my x bar right down the middle. And what was their average? We're saying that their average height is 65 inches, right? Right here is my x bar. Okay. And then remember that we're going to do that whole standard deviation thing. So we need 1 standard deviation, 2 standard deviations, 3 standard deviations, and they should be about the same width. Sorry about that. 3 standard deviations above. Each of these bars, so to speak, is 1 standard deviation wide. So what does that make this? 2.5 inches wide, right? So right here on this mark right here, let's think about it. It's 65, and we're adding to it 2.5 inches. So that's going to be what? 67.5. Okay. So all the people who are within 1 standard deviation above our average here are 67.5 inches to 65 inches, right? Okay. What about 2 standard deviations? These would be, again, still normal expected values. Well, when I add 2.5 inches to 67.5, I get 70. Okay. So again, these would be considered normal. Anybody from 65 to 70 on the above the mean side of things. Those are still my norms, and they're still expected, and there's no outliers in there. But what about for this 3rd standard deviation? 70 plus 2.5 gives me 72.5, right? Right there. Okay, which means anybody that's above 70 inches would be considered an outlier for sure, but anybody above 72.5 is above 3 standard deviations, and they're definitely an outlier, right? There's no question. So Miss Susie's way out here on the tail. She's a 73-inch tall woman, so they could consider her on the tail here. Definitely an outlier. All right, I want to do this same math but going in the negative direction, so we need 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. And again, these should be about the same width. Sorry about that. It's just weirdness. All right, so how do I get the number for this breaking line here? It's 65. The standard deviation is 2.5 inches wide. So 65 minus 2.5, is that what y'all got? So that's 62.5. Okay, so on the short side of things, like I am, if you were 62.5 inches, you're still within 1 standard deviation, you're okay. What about here for 2 standard deviations below? Subtract 2.5 inches, 60. Okay, no problem. So what we're saying is anybody who is 60 inches tall to 70 inches tall, those people are within 2 standard deviations of our average here, and those people are normal. No worries. Okay, no outliers, no issues. But what about down here below 60 inches? Anybody below 60 inches tall would be considered an outlier. And right here on the 3rd standard deviation would be what? 2.5 taken away from 60, so what's that? 57.5, right? Okay. So if we had somebody else, say Susie Hugh, who was 54 inches tall, she'd be on this tail down here, and she'd definitely be too small, too short, outlier, that kind of thing, not an expected value. So we'll have to worry about that later, I guess, if we want to do those. Okay, so this is what that would look like trying to find the breaking points for when you know you have an outlier and when you don't. For sure we're okay between 60 inches and 70 inches. All of these values are within 2 standard deviations of the mean. They're okay. Okay, anything outside of 60 to 70, not okay. All right, so here's the question. Whenever we start dealing with the, again, remember our rule, it's the 68, 95, 99.7 rule. That's what it's called. Okay, so here are a couple of random questions, and this is how you would be asked to utilize this particular set of data and this particular rule. So it says, what percentage of women are between 65 and 67.5 inches, according to this particular model that we have going. So 65 was my average, 67.5 was my first standard deviation, so I'm looking right in here at my first standard deviation. They want to know what percentage is in here. Well, we know within 1 standard deviation is that 68%, right? But I have 2 bars there, so how do I figure that out again? 68 divided by 2 is what I hear in my head. So the left-hand side is 34% and the right-hand side is 34%. So now when I look between 65 and 67.5 right here, what percentage of women fall in that category between 65 and 67.5? 34%, right? That's my answer. Okay, so those are the types of questions they might ask you. Okay, what percentage of women are between 60 and 62.5 inches? And notice for our sakes, hopefully these numbers they're giving me are actually the breaking points that I already have on my graph between 60 and 62, right? Percent right there. Well, remember that was the 95% because it's within 2 standard deviations. So I already have 68% taken care of. So we did that arithmetic already. There's no need to redo it. I've already got it. So I've got it over here. And we know that that guy right there within 2 standard deviations was 13.5%. Okay, so I've already done it once. There's no need to do it over and over and over again. If you want to, you can. You can do the 95 minus the 68 divided by 2. But that's actually on both sides, right? Gives me the 95%. So the answer here is 13.5%. Okay. Here's a real quick question. What percentage of women are below 65 inches tall? 65 was my average, right? Now you can go through and you can figure out both of these two sections here, or we can use the number that we had. It was 2.35 and 0.15. And then you can add up everything that's there below the X bar, but I'm telling you now, and I'm going to do it just to double confirm the math, but I'm telling you now, we should know what that number is. 34, 13.5, 2.35, 0.15. Yeah, we should know what that number is, and my math confirms it. 50.00. 50%. Why do we know that? Why did I know that before I did it? Below the X bar. This is my line of reflection, right? This is symmetrical. Okay, this is a normal distribution. This is the halfway mark. This is the mean, but we know this is supposed to be normal data, and if we did it right, it's also my median. What's a median? It's the halfway mark, right? So if I did it right, that mean and that median should be the same thing, which means there's 50% of my data below the mean. Always the median, but in this case they're the same thing, and there's 50% of my data above the thing. And if you add all those up like I just did on my calculator, indeed, it does work out, which is what we want to see always. Alright, so we can do stuff like this, and what you'll see is, I can give you these numbers all day, but what you'll see in the book or in the homework set is that they'll shade like this and say what percentage of my data points are shaded now. Okay, well we know it's everything that's below this mark right here. Okay, so it's below 1 standard deviation below the mean, and we know that these percentages are 13.5% and 2.35% and 0.15%. So we can figure out what those shaded portions are. Let me do that real fast because I just threw that one out there. I haven't done it yet. Okay. 16%. Yeah, I should have known that. This all adds up to 1, right? 1 percentage point. So 16% of my data is below the 62.5 inches here. Okay, or that's how much is shaded in there. So you'll see these problems where they just shade part of the graph and they want you to kind of figure out what it is. Okay. All right, so here's a weirdo one. Yeah, let me get you a couple of these. Okay. So far, I've been super, super nice, and everything that I've done has fallen exactly on one of the standard deviations. And if that's the case, then those problems will be very, very lovely for us and we won't have to worry about it. However, what about this guy up here? The one with Susie. She was 3.2 on her Z-score. Above, right? So she's 1, 2, 3. She's somewhere in here. Okay? Susie. Okay. Now the problem is that for our stuff, whenever I'm dealing with right on the standard deviation, it's very easy for me to figure out exactly what it's called percentile she's in. So what percentage, here's the question, what percentage of women are below? Okay, for instance, the one that I just did was 62.5 inches. Oops, not percent. 62.5 inches. Well, we did that math. It was this one right here. 62.5 inches. It was this arithmetic right here. 16.0%. Okay, that's lovely. Okay, that's all nice and good, but that fell on a standard deviation. Whenever I say what percentage of women are below Susie's height, which was 73 inches, okay, that forms a problem for me. Because she's up here above the third standard deviation, right? She was at 3.2. Above the X bar. Okay? And that doesn't break evenly, so there's no way for me to tell just by looking at my graph. Okay? That's when this lovely thing called a Z-score table comes in. Okay? Her Z-score was 3.2. Okay, and that is an uneven number as far as how many standard deviations. So that's when this lovely thing called a Z-score table comes in, and I will provide it for you. If you need it on a test, it'll be there, and so on and so forth. Okay, there are 2 pages of this. One is, if you can see this right here, positive Z-scores, which means if here is my mean, they've got it marked with a 0 because that's 0 standard deviations at the mean. The mean is the mean, so it's not above or below. It's 0. So positive Z-scores would be on the right-hand side. Okay, that's what we've been doing. Susie is on the right-hand side. She's way over here somewhere, right? And then the other table is for, if you can see it, negative Z-scores. So again, here's the average in the middle. Mean is 0. It's neither above nor below itself. And these guys fall on the left-hand side of the mean. So they are negative. They're on the bottom side. And you can see, look here, they've shaded in below this portion. Well, that's just a little bitty bit, right? Because it's on the left-hand side. So how much is below that? Not much. But on the right-hand side, because these guys are above the mean, we can see a huge portion of the graph is shaded in, right? So let's see. Susie's score was 3.2. So here's how I use this. My Z-score is the first column, and I follow it down until I find 3.2. Now we're fortunate with Susie because she's actually 3.2 exactly, so it won't be too bad. But I'm going to follow all the way down till I find my Z-score, or the whole number in 1/10, okay? That's in this first column. And then what happens is, you can see, 100th, what if it was 0.01, what if it was 0.02, 0.03, 5, 4, 05, 06, 07, 08, 09. Well, why doesn't it have 0.10? Because if it was 10, it would go to the next guy, right? We wouldn't need 3.2 anymore. We'd go to 3.3. Okay. So I just need 3.200 because it was exactly 3.2, right? And here's my decimal. So Susie is 0.9993. That's the portion of the area that is less than her. Percentile according to the z-score table, okay, is 0.99, what was it again? Sorry, 93. Okay, now the problem is this is out of 1. Okay, this is not a percentage. If you want to make it into a percentage, you need to shift your decimal 2 places, 99.93%. Okay, so her percentile is the 0.9993. Okay, that's the z-score value, the z-score table value. Okay, and what that tells me, her actual z-score was 3.2. Here's her percentage, so that tells me what? 99.93% of women are shorter than Susie. 99.93% of women fall below Susie's height. Okay, they're shorter. They're on the left-hand side. That makes them shorter, right? Because we go in numeric value here. Okay. All right, so some of these become pretty easy to work out. I'm going to just show you one more example, I think, and this video is getting kind of long, so then I'll stop for it. Yeah, some of these get pretty easy to work out. You just are told, right? So, for example, you're just told that the average is 70 and the standard deviation is 11, and my data point is 85. What's the z-score? That's what it wants to know. Well, that's pretty easy. You're just going to plug it into that formula. So go find your z-score data or formula, x sub I, z equals x sub I minus x bar over the s, right? That's your data z-score formula. You'll memorize it pretty quickly once you use it 10 or so times on a homework. Okay, data point minus the average, divide by the standard deviation, right? Okay, do that math. That's 15 over 11, 1.36. All right, so my z-score is 1.36, but that means he's 1.36 standard deviations above average, right? Above the x bar. That's what that means. That doesn't tell me, so if the question is, what percentage of data points fall below, that doesn't tell me. Okay? That doesn't tell me at all. So in order to find that, I'll have to go to the z-score table. Okay, and that's where it just becomes a matter of being able to read the z-score table. I need 1.36. Okay, so the first column, here's my z-score, the first little bit, 1.3. I need 1.36. So what I'm going to do, sorry, I know you can't hardly read it like this. I'm going to follow this line over until I get to 1.36. All right, and that value, if you can't read it, I know it's small and I don't want to take my fingers off to focus, that value is 0.9131. Or we know that that's 91.31%. So you can see how this gives me uneven percentages. It's not those nice round ones that we're getting from where it falls exactly on the standard deviation. So I'll be able to see that, oh, 91.36% of the data points are below him. Well, think about it. If it looks like this, and here's my x bar, and this is one standard deviation, this is one standard deviation. He's somewhere up in here, right? In the middle, he's 1.36, so he's somewhere in between one standard deviation and two standard deviations. Then all of this area in here, down below, is what's below him, right? So that's a pretty good chunk of my graph that I'm shading there, okay? All right. Okay, one more quick little thing. I hope you've noticed that this works for both positive and negative z-scores, right? So if it's bigger than 2 above it, then it's an outlier. If it's bigger than 2 below it, it's an outlier. So we have to be a little bit careful. Again, here's my x bar. 1, 2. 2 standard deviations above, 1, 2, 2 standard deviations below. These guys on the tails, those are my outliers, right? So I need to be a little bit careful whenever I talk about it, because I just can't say 2 standard deviations above. I have to say above or below, or I have to say 2 standard deviations away from the mean, or something like that. So a lot of times what you'll see is, if we use this as our z, which is the standard z-score formula, if the absolute value of z is less than 2, is no outlier. Okay, but if the absolute value of z is greater than 2, then we have an outlier. Right? So basically, remember, absolute value makes that thing positive. So if we're bigger than 2 on the positive side or less than 2 here, so in other words, if it was that problem that we did a minute ago with Susie was 3.2, well, the absolute value of 3.2 is 3.2, right? So that's bigger. But what if my z was negative 3.2? Well, the absolute value of negative 3.2 is also 3.2, right? So you have to think about that. What an absolute value does is it tells me the total distance from 0 here, and 0 is my average. So the total distance. So I want this distance to be bigger than 2. So I want these things to be way down here on the negative side, or if it's bigger than 2, then way up here on the positive side. All right. So I hope that makes sense to everybody. Yeah, I think that's about it. So if you have questions about this data, about normal distributions, about z-scores, then let me know. Otherwise, I'm happy to report we are done finding ways to find outliers. Those are the 3 major ones in the course, and we're just going to be applying that throughout the rest of the semester. All right, have a great one.